Much the same way we did for mirrors, we can use a ray tracing diagram and some geometry and trigonometry, well, just geometry to find what's called the thin lens equation. A thin lens equation makes the assumption that this lens is, well, thin, as you might guess. In fact, it assumes that the lens is infinitely thin, which isn't true, but the thin lens equation still works very well for lenses until they get really thick. So here, if we look here, this is our object, and our image is formed over here, image. And if we look at these two triangles right here, these are the same angle, and then these angles are the same, and the other angles are the same. So we've got similar triangles again. And this is our object height, this is our image height, and this right here is the distance to the focal length, and this is image distance minus focal length. Okay, and from that we can write a ratio. Just using similar triangles, we can say our object height over minus our image height is equal to our focal length over image distance minus focal length. Okay. Similarly, over here, same object height, same image height, and this is our image distance, this is our object distance. These two triangles are similar, so we can write object height over minus image height is equal to object distance over image distance. And from that, we can, again, find an equation for the lens. We can say that our focal length over yada yada, that is the case, and we can follow a similar process as we did when deriving our mirror equation. Say 1 is di times f over do times di minus f, and then we can factor stuff out. We can say di times f over do times di, and this would be 1 minus f over di, and we can also we can pull out a do over here, kind of. Yeah, we can just leave it there. Okay, so di cancels out, and then going from there, we have 1 equals essentially f over do over 1 minus f over di. We can move that over to the other side. 1 minus f over di equals f over do. Add that over. 1 equals f over di plus f over do. And then divide out an f. And what do we get? 1 over f equals 1 over do plus 1 over di. If I do, I die. So it turns out the thin lens equation is exactly identical to the mirror equation. Exactly the same. Which I guess is good, because it means that physics works. So this is the same as the mirror equation, though some of the sign conventions are a little bit different. And if you look at page 932, it gives sign conventions for lenses. So the equation for lenses versus the equation for mirrors is the same. The magnification for a lens is also defined the same way it was for a mirror. It's minus di over do. So that's everything for lenses, and it's very similar to the equations that we had for mirrors. We also want to talk about dispersion. That's another effect that's related to refraction and whatnot. So refraction, it depends on the index of refraction, so it depends on the materials in question. But it also depends on the wavelength of the light involved. In general, or rather, well, the frequency is really the salient property, but those are for light, those are so closely related because their speed is c. But in general, as the frequency of the light goes up, the refraction also goes up. Higher frequencies refract more. Okay, and because higher frequencies refract more, some interesting things happen. That's why if you get a prism, which is just essentially a lens, but it's shaped like this, light coming in would bend toward the normal here, and then bend away from the normal, and so it would bend more. But the different colors of light will refract different amounts, and so a prism separates out the light, and you get that sort of rainbow thing going on. Dispersion is also responsible for actual rainbows that you see in the sky. So what's going on is that there's, you've got, this is a raindrop, and you've got light coming in from the sun, and this light from the sun has all different colors in it. It's essentially white light. Okay, and when it comes into this raindrop, it refracts, it bends. However, some bend more than others. The violet light and the red light bend different amounts. They're split up a little bit. Then, some of this light has total internal reflection off the back of the raindrop. And this red light, it bounces back at some angle. The violet light bounces back at a different angle. And then they both refract again when they're heading over to your eye. And so now they've separated out. We've got violet light up here, red light down here. So if you're sitting here and you're looking over here at a place where it's raining, the sun has to be behind you for you to see a rainbow. And the light's coming from the sun. And if we've got rain going on over here, up here the violet light's going to be going off violet's going to be at an angle down here, whereas the red light's going to be angled more down. So here you might see the red light, whereas at some point lower, the violet light's still going to the same angle, and so is the red light. But here, it's the violet light that's hitting your eyes, and up here it's the red light that's hitting your eyes, and so in between, then you see all the different colors of the spectrum. And so that's how you see a rainbow, and you see it, you might know Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. You see the red on top and going down to violet on the bottom. So that's how rainbows are produced, through this dispersion. It's caused by the fact that different wavelengths of light refract differently. Another important application of lenses, the book talks more about this in chapter 27, but we're not going to do chapter 27, so I wanted to discuss it now, is just human vision in our eye. So the way our eye works, basically the front of our eye acts as a lens, and then in the back of our eyeball, they're on what's called this is called the retina. This lens focuses the light coming into our eye, and it forms an image on our retina. However, if there's something wrong with your lens, sometimes people have images, but they don't form on the retina. They converge. The focal length of this lens is in front of the retina, and so by the time the light gets to the retina, you've got a blurry image. Okay, if light focuses in front of the retina like this, if your focal length is too small, then you need a diverging lens. Because if you put a diverging lens in front of your eye, it'll spread those light rays out a bit before they hit your eye, and then you can form that image back on the retina. And that means that you are nearsighted. You can only see stuff up close. And so you need this diverging lens to correct that. And the diverging lenses don't have to be shaped like this. Actual glasses are what's called a meniscus lens, where they're kind of shaped like this. They're both sides are curved, but then they're wider. I didn't draw that very well. They're wider on the outside than they are in the middle. And you can see that, here are my glasses. If you look at the lenses, you can see that they're thicker on these edges over here than they are in the middle. They are diverging lens. I am nearsighted. In the opposite case, and most of you guys are probably nearsighted, those of you that have glasses. If the image tends to form behind the retina, again, things are blurry, but you need a converging lens to fix that. And that is, if our f is too large, then you need a converging lens, and that is being farsighted. And this, typically, most of you guys probably aren't farsighted. This tends to happen as you get older. People need reading glasses. They can see things far away, okay, but they can't see up close. And this really isn't like, so the lens in your eye actually moves around. It's a flexible lens, and it stretches or compresses to get the correct focal length to see whatever it is you're looking at. So the issue isn't that the lens is wrong necessarily, but that it doesn't properly expand or contract. It doesn't change its focal length properly. So if you're nearsighted, then your lens doesn't adjust enough. It doesn't. You need less a lens with a longer focal length to focus rays coming in from far away, and so your lens doesn't stretch out enough if you're nearsighted, and it doesn't compress enough if you're farsighted. That's just an application of lenses that's important to our daily lives, especially those of us who wouldn't be able to see without our glasses or contacts.